Back to the 11th session of our socket programming in C laboratory series. Today will be about multi-threading TCP server and TCP client. So let's first try to understand get the theoretical understanding of the threads. So for that we will be using processes as a comparison. So what are the drawbacks of processes compared to threads? First of all, processes are burdensome. Whenever you try to create a process, a lot of resources of your computer will be wasted. And once a process is created, the context switching between processes will degrade the performance of your computer, because when the CPU is executing the instructions, as each process is separate from each other, all the context like variables, values are different in each process, right? And because the CPU has to provide a concurrent programming while it has to execute all instructions of all processes that it's currently running at the same time at any given point, what processor has to do is it has to switch between one process to another, and that triggers context switching, and which will be difficult when you create separate processes to handle TCP, the computer network's needs, right? So therefore the processes become burdensome. And the next thing is data exchange between processes is difficult. As we have covered the IPC, interprocess communication, we have seen that it's not an easy task to make two processes to talk to each other. So because no data is shared between two processes, as they are separated from each other in a process level, we have to use some kind of IPC methodology to make two processes talk to each other, and that's also an extra work, and that's not an easy task. And here comes, when we try to tackle these problems, here comes the threads. So what are threads? Threads are the smallest possible subsequences of instructions that share data, code, heap, etc. of the same process, the resources of the same process, or so to say, primary thread. And that can be managed independently from each other by a scheduler. So basically the resources of the process are shared between the threads that are created within the process. So you will get the better understanding in the next following slides. But for now, just memorize that the threads are the smallest possible sequence of instructions, and they share the resources of the same process. In other words, the data, variables, constants, the context, and functions are shared among all the threads because they're created within a single process. And now we are not dealing with multiple processes anymore. We're dealing with a single process, but it creates multiple threads. And this will lower the performance degradation due to concurrent programming and eliminate the need of IPC compared to multi-processing. So let's try to see how it looks like on an operating system view. So whenever you're creating multiple processes, what you're saying is, an operating system, make one more process and run these instructions in it. So that's basically what you're saying. And in an operating system's perspective, that process will be created as another block. And when you say to an operating system, please create a thread within my process, what you will be seeing is the block will not be extended anymore, the process will not be created anymore, but within that process, small lightweight threads will be created. So therefore, you can see that the amount of work done by an operating system when you create processes and when you create threads. So that's the difference. The thread is the smallest subsequence, the smallest sequence of instructions that can be put as a group in an operating system. So that's the smallest one. And when you use smallest one compared to a bigger one, of course it's better from the performance perspective. And so how is the data shared between threads, and how was it shared or not shared in processes. So first, to understand that, we have to take a look at this. The processes are created from an operating system's perspective, because what operating system has is it has processes, right? It's divided into processes, and those processes have, each of them have their own data, their own heaps, their own stacks. This means the processes are completely separated from each other, meaning they do not share any data. They do not share any context with each other. They are completely separate things. The processes are completely separate and nothing is shared between them. And when we move to the next level of instructions, sets of instructions, that's within those processes, right? That's inside the process. It looks like this. Those things, which are threads that are created inside the processes, will have access to all the data, all the heap, all the stacks within that process, because they're sharing everything, right? And therefore the threads are created from the perspective of the process, because it's within the process. So basically an operating system is split into processes, and processes are split into threads, and that's the smallest thing that you can split. And this means the threads share the process's resources. Therefore, the context switching becomes much easier compared to the case of processes, because the smaller context, smaller resources are being switched in the perspective of CPU. The CPU is not switching the big processes; it's switching the small, lightweight contexts. So therefore the performance will be much better, and that's how the data is shared between the threads. Alright, in order to create a thread, you have to include this little pthread.h header file, and then you have to use this function called pthread_create, which accepts 1, 2, 3, 4 arguments. And the first one is the thread ID. So basically it's an integer that creates a thread and just passes the created threads ID to this value. And you can specify a lot of attributes like joinable, like detachable and stuff, but for now we'll be skipping this point, the attributes. And then the next thing is what that thread has to execute, because whenever you create a thread, you have to specify, you have to tell, I want this thread to be running this function, right? So that function is specified as a third parameter, and then the last one is the restrict argument. That's the parameters. That's the parameters that will be provided to the function that you specified here. For example, your function can be a sum of two values, and the parameter has to be those two values basically. And let's take a look at the example, creating and running threads. So whenever you create a thread, you have to check the result that's coming out of it, because if it's not equal to 0, that means there has been an error while creating a thread. And when the result is success, the value will be 0. And this is an example where we are just creating a simple thread that prints out the text running thread. The amount of times that you specify as an argument, which will be the arg variable, and from the arg variable we're getting an integer, and that integer is specified when you created the thread. When you created that thread, the last argument was thread param, right? The thread param is actually a variable, an integer, which has a value of 5. And what we're doing is like we're retrieving the address of that variable, converting it to a void pointer, so that the operating system, so that the process could call that thread with a just simply void pointer without knowing the type of that value. You can provide string, you can provide whatever, but you have to convert into a void pointer. So we are converting it back into a counter, the value, which will be 5, and we're looping just the times, the value times. So that's 5 times. We are looping 5 times, sleeping for 1 second each time, and printing and running thread. And then so the result is it's printing out 5 times the running thread text, and the thread is finishing. And after that we have specified here that the main the process itself, the main thread, sleeps for 10 seconds, and after the 10 seconds it prints out end of main. So basically that's why after 5 seconds plus 5 seconds we're seeing end of main. So let's compile and see this ourselves. So that one is the thread1.c file. Let's copy it inside our C drive, cygmin folder, right here. And let's first take a look at the source code to confirm that it's matching. So inside the main function, what we're doing is we are creating one variable to store the thread ID, and we are creating that parameter that I've just explained to you, and we're calling pthread_create by providing the address of this variable that will store our thread ID, and we're providing nothing to the attributes, and then we're saying that thread will be running this function, and that function is the name of the function right here. And I will explain why we did void pointer. Actually, we don't have to do it right now, but just memorize it for now. I will explain why this is like this void pointer in the next source file. So we are providing that function, thread main, the name of that function, and then we are saying it will accept this parameter. And that parameter has a value of 5, which is integer. And provided that this function has returned 0, which is not the error case, we are sleeping for 10 seconds and then printing out end of main. And then that function is retrieving the value of the argument, which will be 5, and counting 5 times, printing out sleeping for 1 second, and printing out end of thread main. Oh, this is something extra because that wasn't inside slides. But for now, let's just put this one. After 5 seconds, it will also print. When the thread terminates, it will print out that the thread has terminated. So let's compile and see what happens. gcc-o. One more thing that I forgot to tell you that is, don't forget this flags. There's one more flag that I will explain now. LP thread, it's for the pthread.h file that we have specified. Oops, pthread.h file that we have specified here, as there is a linking stage when you compile a source file with GCC. The symbols that are created here will not be known. For the compiler will not know the symbols that are defined inside here, inside the pthread, because that's on the level of a linking stage before the compilation stage. And in order to tell the compiler to include the pthreads symbols inside the linking stage, we have to tell okay, first of all, thread1.c, we have to say lp thread, and we have to actually give this flag as well. That's called d-reenter. That basically when you're working with threads, some functions have two versions of them. One version is thread safe, and the second one is not thread safe. That's thread safe will be explained a little bit later, but for now just please memorize these two flags. They're not difficult, right? Just lp thread and reentrant, that's it. So let's compile the file, which was printing out running thread 5 times and printing out end of the thread, and at the end, after 10 seconds, it was printing out the end of main. So let's compile that file, which we have just done, and let's run it, thread. When we run it, we'll see each second printing out the running thread 5 times, which is the last one, and the thread has terminated, and after 5 more seconds, the main will also terminate. So basically that was an example, that was the basic example of how threads are created and executed. Now that we know how threads are created, there are a little bit more things that we have to know in order to be able to use it in networking applications. Okay, the thing is that as the thread is created inside the process, your thread can be executing a large task. For example, downloading 1 GB of a file, for example. You might be downloading a movie. And while the thread is downloading a movie, your process might want to terminate. For example, if your downloader is downloading that file and you click that little X button on the left side, what your process does is just kills, the operating system kills that process. And when it kills, all the threads that are inside the process will be also terminated, like the example on the right side. As the process is going to be terminated, everything that is inside the process will also be terminated. What we want to do is actually we want that process to be waiting for that thread to terminate. It's like an example of the zombie process, if you remember. But it's a little bit different because we are not creating separate processes, but what we're doing is we are elegantly elegantly waiting for the sub-thread to finish. And after that, we are terminating that process. In case we want the created thread to finish, we could use sleep function in the process, but this has limitations, not a good practice. It's not a good idea to make the process just sleep for some time and then expect that thread has terminated, because it depends on depending on the operating system, the thread might be running slower, much slower than the process itself, than the main thread itself. And that thread might be executing, downloading, for example, 20 megabytes of data slower than the main process downloading 1 gigabyte of data. It might be, no, it's actually exaggeration, but still, that thread might be executing slower than your sleep. And that means your process will be still terminating before the thread has finished its job. What we want is, when the process terminates, the thread execution will also be destroyed, blah, 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 blah. What we want is our process to wait for the thread to finish. And that is done by making a call to this function called pthreadJoin. And what join function does is it will freeze the calling process itself until the specified thread with the thread ID finishes its routine. Join means basically join that thread that I specified to the main thread. And when they're joined, when the two threads are joined, basically the work, whatever is being processed on the main thread, will be frozen until that child thread finishes its job. And then the result that's coming out from the thread that we want to finish, is going to be stored inside this status variable, which we will provide ourselves as a variable. And this is the example of how the code is written. And let's first take a look at the graph, how it looks like. We are first creating a thread by making a function call of pthreadCreate. And then what we're doing is, on the process side, we are just joining that thread. That means whenever that thread finishes its job, I want to continue executing, because the next thing that I want to do is to kill the process itself. And when that thread terminates, it returns some message, and that message will be read by the process and printed out, or whatever you want to do. For example, file has been downloaded or whatever. So that will be done, and then the process will be also terminated. So when you compile and run that file, what you'll be seeing is the running thread message being printed out 5 times, and then I think you can see it, but still, the last line is thread returns a message of hello, I am thread. That's the last line. That means the process has been waiting for the thread to terminate, and that thread has returned that message, hello, I am thread, and then the process has printed out that hello, I am thread message. And the next thing is the content of the thread. Let's take a look at the source code first. We're still providing the value of 5 to the thread that we are creating, and then the one additional step we're doing is we are joining that thread. Instead of sleeping for 10 seconds in the first example, if you remember, we are not sleeping for 10 seconds, we are joining. And after we join, we are simply just printing out whatever that has come from that thread as a result, that message. we are saying thread return message, hello, I am thread. And then we are freeing the memory that was created by the thread, and we are just terminating that process without sleeping. And the content, the routine of the thread is just very simple, like in the previous code. We are getting the value of 5 as a CNT, and the one additional thing what we're doing is we are preparing a memory area which we will be returning as a result by allocating a memory of size 50 bytes. And when we have that 50 bytes, we are copying the value of hello I am thread to that memory space and sleeping for 5 seconds, printing out the running thread each time and returning the memory area that we have written this value into. We are returning that, and the note, why the thread main's type was void pointer, because we are using it as a return type, because we are returning a memory area of type character pointer converted into a void pointer. Because the returning value has some type, we are making it void pointer. And we are reading that value as a thread return, and that thread return is a void pointer. And when that thread join has passed, that means the thread has terminated, we are printing out the value of that thread return memory area, converting it into a character pointer, converting it back to character pointer. So now that it's clear, let's just copy that file and try to compile and see the output. That is the thread2.c file. Let's copy it inside our CYGMIN folder, and let's confirm that the content is the same. So we have the thread underscore main function defined here and implemented right here after the main function. And what main function is doing is exactly matching with the slides. It's creating and joining, after which it's printing out the resulting value that's coming out from the thread routine, thread main. And that thread main is what it's doing is it's getting the argument, converting it back into a value which will be 5. This will be basically 5, and we are creating a memory area. We are allocating a memory of size of character multiplied by 50, which is 1 byte multiplied by 50, that means 50 bytes. We are allocating 50 bytes, so basically it's not necessary. And allocating that memory and storing it inside this pointer, and copying the value of hello I am thread to this pointer's memory area, and then returning that as a void pointer. And that is accepted by the thread return, because we have joined that thread and we know that the thread has terminated after this. With this result, we are printing out that as a character pointer. That is it, very simple. Let's compile it and see the output. gcc-o thread2.c lp thread d rank, and let's run that thread. We have seen like 1, 2, 3, 4, 5. It terminates with this message. We have seen that the thread is giving back that message, and the main thread is printing out that message. So basically this shows how the threads can be managed by a process, which is also very simple, just pthread join. So basically there are 2 functions, which are, the first is pthread create, the next thing is pthread join, and voila, you're good to go with processes. So the next thing is the idea of how threads execute large scale jobs, for example downloading, like I told, downloading 1 GB of file. The idea of threads relies on making threads do all the heavy work and submit the result to the caller, to the process, to the main thread. And the caller gathers all the results from the threads. For example, your process might want to download, for example, 5 files at a time, just at any given point of time. You might want to download all the 5 files which have like large sizes, 1 gigabyte, 2 gigabytes. And for example, the first thread is downloading 2 gigabytes of file, and then the second thread is downloading 1 gigabyte of file, for example, let's say that. And when we run it, it will be executed before, and then when we run the second threads and then call thread pthread join, it will also be finished after a while. And then, for example, let's say it will be the results from the first and second threads will be merged, and we have the 3 gigabyte of file, right? And this example is actually an example of summing up values between 1 and 5 with one thread, and summing up the values from 6 to 10 on another thread. That's just simply the sum of all numbers from 1 to 10, just being split into 2 parts and like dividing and conquering. One thread is summing up all values from 1 to 5, second is summing all values from 6 to 10, and the process, the main thread, is collecting the results from those 2 threads and just taking the sum of the 2 values and printing out the result as the sum of values from 1 to 10 is this. So that's the idea of dividing and conquering, how it can be used by the threads. So what we're doing is we are splitting the range into 2, from 1 to 5 and from 6 to 10, and we're creating 2 threads, 2 separate threads. And the 2 threads will be running the same routine, but with different parameters. First of which will be range 1, second of which will be range 2. And then the results will be different, right? The result will be the value of sum. So here we are not returning the resulting value as the result of the routine, but we are creating one global variable, and that global variable will be updated by the threads. So basically the first thread will update the value of sum, which will be updated as a value from 1 to 5, and then the second will update it from 6 to 10. And then at the end, the process itself will join those both threads. That means both threads will be finished by this line of code, and we're printing out the value of sum. And what the routine does is it starts from the first value of the argument, which is 1 in this case. The second will be the first, the index 1, that will be 5. So we have the start and end, which is 1, 5. And while the start is smaller than end, while the value of 1 is smaller than 5, we are summing the value of start and incrementing the value of start. That means 1, 2, 3, 4, 5, and then at 6 it will finish. So the sum will be incremented by 1, 2, 3, 4, 5. That means the sum will be having the value of the sum from 1 to 5. And then the next one will be the sum from 6 to 10. And if you try to calculate the sum from the number 1 to 10, that will be 10 divided by 2 multiplied by 10 plus 1. That means 5 multiplied by 11, which is 55. So the value is correct. Let's try to compile the source file and see it ourselves. So that example must be thread 3. Okay, thread 3.c file. Let's copy it inside the cygwin folder. And let's confirm that it's matching. So it has 2 ranges, it's creating 2 threads, giving 2 values, joining both of them, and printing out the result. And this one is getting the starting and ending. It's looping through all values, incrementing the sum, storing it inside a global variable, so everything is matching, right? Let's compile the file and confirm. gcc-o thread 3.c lp thread d range and thread. If we run it, the result is 55, and that result is the value of sum, which is this one. And if you do this, and if you print this out 2 times before joining and after joining, it will not be 55. It might be, for example, 1, it might be even 0, it might be, I don't know, the value of 1 plus 2 plus 6 plus 7. I'm not sure. Let's try to compile and see. So it's basically 15. It's just the 1 plus 2 plus, I don't know, it's like maybe, I'm not sure, like it's some value, right? It's just sum of some values. So that means the threads have not yet finished their execution, and it will be executed later after join, and then we have the complete result. Therefore, we were doing the pthread join function call. Oops. So the next thing is the problem that might occur in this case when we were updating a global variable that was shared between 2 threads, right? So for example, what kind of problem there could be? The 2 threads might be updating the same variable, right? The expected behavior will be as the example above, as the illustration above, when the first thread is incrementing the value by 1, and then the second thread is also incrementing the value of the global variable by 1, and starting from a value of 99, it must be 101 after adding the value of 2, right? Incrementing by 1, 100, incrementing by 1, 101. But the thing is, the problem with shared variables between threads is that when you update, when you try to update the value of a global variable at the same time by different threads, because there are 2 operations in incrementing in which are reading and then updating, the reading, incrementing, and then storing. There are 2 operations, reading and storing, right? And there is actually one more operations inside that CPU does, is actually incrementing the value itself, because it has to get the value from a memory space or cache to the register and update the value of the register by 1, incremented by 1, and then store back inside the cache or the memory, your RAM, your main memory. So there are basically 3 operations, right? And when the threads do it like at the same time, when there is a notion of concurrent programming with threads, one thread might read the value, which was 99, and the second thread will read the value and store the value. Like the second thread is already updating, right? And doing all the 3 operations at once. And the first thread did not know that the value was updated, because it just read the value, updated the register, and then it's trying to store it back. So the expected execution will be having different value than the unexpected execution, which is a realistic case. So it's like expectation and reality. So this is an expectation and this is a reality. So this can be a reality. And so in order to handle this, what we have to do is we have to work with such things called as critical section. We have to specify that that one incrementing operation is a critical section, and that would mean the CPU will not allow other threads to run their code when it's going through a critical section, which is a solution to the simultaneous access issue. So there will be no simultaneous accesses like in this case, or in this case, there will be no simultaneous accesses inside a critical section, so one thread at a time. That would provide us this kind of a behavior, like expected behavior, because one thread is locking that global variable, that instruction set, so that the 3 operations will be executed by just a single thread, and then the second thread will be stopped, will be waiting for the first thread to finish to enter that critical section. And that's done by for that, let's first take a look at the for that, let's first take a look at the problem, how this problem is occurring. For example, let's say our thread, we have two threads which are adding which share one global variable of num, and that those two threads are executing two different operations, first of which is incrementing by 1 and second is decrementing by 1. And when the value of num, if it starts from 0 and if the number of iterations is the same in the two threads, we expect the value to converge to 1, right? For example, it can, from the beginning, it can be 1, 2, 1, 2, 3, 4, and then it coming down to negative, and then just fluctuating a little bit because there is one thread incrementing it and the second thread decreasing it. So it has to converge into 0, right? And if this problem of simultaneous accesses occur, the value of num should not be 0 by the end. Let's take a look at the source code, which is thread 4.c file, and confirm that we have that kind of issue. So it's basically a very simple example where we are creating two different threads, one of which is incrementing and second is decreasing. And we are joining those two threads, and actually the num thread is equal to, oh, it's 100, okay. So we are creating not just two threads, but 100 threads, and each even thread is going to be increasing the value, and each odd thread is going to be decreasing the value. And we are creating 50 threads that increase and 50 threads that decrease the value. And the type, the size is actually long, and long is actually I think 8 bytes. Yeah. So we are printing out the size of long. Okay, 8 bytes. And why I'm saying the size of 8 bytes? Because there could be an issue with a memory, and I want to just first tell you what is actually this 8-byte value, what kind of value it can store, what kind of a memory area we are dealing with. That's what I want to show to you. So the value is as follows. So 2 to the power 8 bytes. That means the maximum value is actually quite a lot, and I think that will be like maybe, I'm not sure how many digits there, but what I wanted to show is like how big value can this num store. And that means we don't have any problem with the memory, because it can store large values. And after we create those threads, we are waiting for those threads to finish, and then we are printing out the value of num, which we expect to be 0 by the end, right? And the thread increment is just incrementing the value by 1, and decreasing is just decreasing by 1 the same amount of loops, so the same amount of iterations. Therefore, we expect the value to be 0, but when we run it, what we will be seeing is as follows. gcc-o thread 4.c. We have to wait for a while because we have 100 threads running, all of which are looping, I think 5 million times or something. It was a lot. Even computer is freezing. So 5, yes, it's 50 million times. That's a lot. That's quite a lot. And why 50 million times? Because we want this kind of bad result. And this is occurring because this many times, I think it's like 433,978 times there have been parallel access problems, like right here there have been parallel accesses, and I want it to be running a little bit faster. Let's make it like 20 and see if we have the same kind of issue again. It must be faster, it must be. Yes, it's faster and we still have that issue. You see, it's decreasing, but still there is a problem of parallel access. If you run it, you will see still a different value, which is not still 0. Because we have a problem with parallel accesses. And how do we handle that? How do we solve that problem? It is solved by synchronizing threads. So basically what synchronizing means is when entering the critical section that I've told you, critical section, you will just simply lock the door to that critical section so that other threads will not be able to enter that area. And that means the CPU will be only working with one thread at a time within your process. And then after finishing that critical section, you will just unlock that area, and then the next threads can enter it. That means the process will become concurrent processing, will still keep on executing concurrently after you unlock it. And when you lock it, your CPU, your process will not be concurrent anymore. It will be just running one single thread. So that's the idea. And the locking operation is with init, and unlocking operation is with destroy. So init is locking, destroy is unlocking. Oh, I apologize, I made a mistake. Init is actually creating the lock, destroy is actually removing that lock, and there is the keywords lock and unlock to the lock the lock and unlock the lock. So we are creating a mutex first with init function call, pthread mutex init function call, and after we do all this operations with the critical sections, we are destroying that mutex. That mutex is basically the lock. So we are locking the mutex and then unlocking the mutex with these two function calls. And let's take a look at the example. What we're doing is we're creating the mutex first, and I want to skip through these elements, and then at the end I want to show you how we are destroying the mutex, the lock. We are creating the lock and then we are destroying the lock, and it's the content is the same, exactly the same as the previous example with problematic simultaneous accesses that resulted in non-zero value, and the increment and decrement is doing the same thing, except it's locking and unlocking the critical section. So basically the critical section is updating the value of num global variable, right? So the question becomes, how do you know the critical section? Critical section is basically the instructions which update, for example, change the values of the shared variables, shared global variables between multiple threads, child threads. So basically that's how you know it. And here the integer I is not the critical section, return is not a critical section, and even the for loop itself is not a critical section. Is actually the updating the value of num variable is the critical section. But this example is showing you two different ways of covering the area of critical section, which is just including the for loop area, and then the second one is including just the global variable updating scope inside that for loop. Actually, this is not necessary because all the whole loop is making the process run one process at a time, and it's not concurrent anymore. It's not the process will not be running all threads at the same time, but only it will finish one thread and then it will move on to the next one, and we don't want that behavior. And in the code itself, what we will be doing is we'll be using this way. We will lock and unlock before and after updating the value of num, and when we compile and run it, the result is actually 0 because that was what we wanted, right? Because the number of incrementing and decrementing was the same. And that is the example of mutex.c file. Let's copy it and open and see that the content is matching. Let's make it still 10. I believe we made it 10 before, right? If not 20. Well, I want to just confirm that the previous time we ran the thread 4 was 10 times, not 100 times, because the mutex will freeze. It will be much slower than the thread 4, and therefore I want to decrease the number of threads still having the same problem. Let's compile the thread 4 and see if we still have that problem. Thread 4.c lp thread d. Yes, okay, we have that problem. So 10 threads is still giving us that issue. And when we change the value of number of threads from 100 to 10, we still have that problem, which we still expect the same problem, which we are solving with the mutex, right? By synchronizing. So we are still creating those 10 threads, 5 threads incrementing, 5 threads decrementing, and we are joining, and then we are printing out the results. And I don't understand why we have this here printed out. We don't need it. And then we are printing out the result of the num, and we are destroying that lock, that mutex. And inside the increment and decrement, we are locking the critical section and unlocking. We're locking the critical section and unlocking. I don't like this implementation, like I told during the slides. Let's just make it like more normal, because for loop is not the critical section. The content is the critical section. So basically we are locking and unlocking the mutex before and after updating the value, and we're doing the same in decreasing as well. And we expect the value to be 0 after running, and I want to tell you that it will be, I think, quite slower than the problematic case. gcc-o mutex not lp thread b run front, and when we run it, I hope it will finish not as slow as I'm thinking, because it will be quite slow. Let's just wait for a while. This pause is happening because we don't have that problematic case of simultaneous accesses, and if it's working a little bit slower, that means it's actually good. Why is it good? It's still running concurrently, but it is not running the problematic case. It's like running as it should, 3 operations at a time, which was retrieving the value, incrementing the value of the register, and storing that value back inside that memory area. And when we do this, it's actually a little bit more. The realistic duration of the execution is actually much more. Therefore, it is slower. And also, our mutex is actually not executing one process, but is executing one instruction, but it's executing 2 more instructions at a time. So it's multiplied by 3, and the same in here as well. Multiplied by 3, multiplied by 50 million. So that many more times it's actually locking and unlocking the mutex. Okay. I am actually losing patience, so what I want to do is actually do this one as the example that was given by the slides. Maybe this will work faster, because the locking and unlocking operations is not just a single operation, so it might be more. Let's see. Okay, the result is 0. So that's what I wanted to show. It's much more faster, because we are locking and unlocking the area just once. And that means the critical section is being executed by one process at a time. And when we remove this lock and unlock, what we will be seeing is the same problem that we have seen previously, which is the simultaneous access. And that Mutex is actually solving that issue by applying the critical section in our code. Therefore, we have the value of 0. So problem solved. Now that we know how we can synchronize threads, we can move on to the last step. And actually, the last step is multi-threaded TCP server and multi-threaded TCP client. And after that, we'll be done. And so, the now current implementation of the multi-thread TCP server and TCP client will be actually a chatting application. So our clients will be able to chat with each other. And this is just actually a subsection, just two functions of our TCP server. One of the functions which handles each client, and second sends message to all clients. And this handle client will be called by a thread that will be created by the parent process, the process itself, the main thread. And the client socket will be provided as an argument, and we will retrieve it as convert it back into an integer from that argument. And then we are going to be reading all the messages that will be coming from the client and sending it to all clients. So, and that send message is actually implemented right here. We will come back to it a little bit later. And after this all is finished, after the reading and sending is finished, and I want to remind you, this is the server part. So after that reading and sending is finished, by one, just simply when one client disconnects, that read will be returning a 0 value, and then when it returns that, that this area will be terminated, after which we have to remove the disconnected client from the global variable that is shared between child threads inside the TCP server. And at this point, we are entering the critical section. So we are locking the mutex and unlocking the mutex after the critical section is done. And inside the critical section, what we're doing is, what makes it critical is that there is a global variable, which is the client sockets array, and we are updating that array. We are checking if this client that has disconnected is at the index of I. We are removing that client by storing all the client sockets on the next to this client socket to this client socket's address, and that means we are just removing that client socket I, which has disconnected, from the array, from the global variable array, variable array, and we are decrementing the client count. For example, if it was 20 and one of the clients has disconnected, it will become 19. And we're unlocking that mutex, and we're closing that client socket and returning null. And what that send message does is, actually, whenever any client sends a message, it transfers back to all clients. So sends to all. We are locking and still unlocking, because this is also shared. The client socket is shared between the processes, between the threads. I apologize, it's not processes, it's threads. Therefore, we are locking the mutex, and we are transferring the message to all clients, and then we are unlocking. So basically, after this, any client can disconnect. And what is the client side doing? Let's take a look. The client side is also creating two threads. And one of the threads is for sending and second is for receiving, and as you guessed, it's splitting IO routines, input and output routines. So receiving part is the input routine and sending is the output routine. So we're creating two threads for sending and second one for receiving, and we are joining those two, and after which we are closing. And whenever the client decides to enter inside the send message case, enter queue, just simply quit queue. The socket will be, the open socket will be closed, and the thread will exit with code 0, after which the socket will not be available anymore. And the receive case, it's running, looping infinitely, inside which we are reading from the socket that is shared between the two routines, which are writing and reading. Inside the reading case, we were closing that socket, right? After closing that socket, if the read routine tries to read it again, the value will be -1, and we are returning, just finishing that execution of input routine whenever read gives us error. So that gives us error when we close it, right? So therefore, when the client enters queue, the whole two processes will finish. That means both joins will come back, and then the main process will also finish. So it looks very beautiful. Let's take a look at the source file and see how it works ourselves. Let's copy the C files inside our COIGWin folder. Let's first open them and confirm that they are matching with the slides. Let's start with the chat server. Inside chat server, we are saying that we want to accept maximum 256 clients. I think that's enough for our case. And we are defining the three functions, which are handling clients, sending message to all, and defining, yes, and error handling, and this is not important one. And we are keeping count of how many clients are connected to us, and we are keeping track of each socket file descriptors of each client socket. And we're creating one mutex for critical sections. And the following are very simple, just like creating variables for server socket, creating the mutex, and providing the address to the server, listening to any connection, binding, listening, and then inside while loop, what we're doing is whenever we accept a client's connection request, we are getting the client socket and creating, we are entering the critical section where we are updating the global variable, and we are unlocking, and we are creating another thread with the client socket file descriptor, with the new one that we have just accepted. So that has to have one thread devoted to that client, and we're running that handle client routine. And we are saying, after creating, I don't want to be joining to that thread, and operating system, please free whatever resources that thread has done, and that is done by detach function call. So that thread will be called detached, so that the operating system would clean up after it finished execution. And then we are printing out that one client has connected and printing out the internet address of that client. And after this whole thing is done, we are closing the server socket, which will never happen because it's while true, right? So let's take a look at the implementation of the handle client function, which is also matching, which is the same thing that I just explained inside the slides. We are getting the value of the client socket file descriptor, and we are creating a message. We are reading whatever is coming from that client, and if it's not equal to 0, which will be the disconnection, right? The close, basically the TCP connection will be broken if it's 0. And while it's not 0, we are sending the message to all other clients. And we are locking, after this whole operation is done, we are locking the mutex, and then we are removing that client from the array, from the global array. We are updating the global shared variable, shared array, that's why we are locking. And then we are decreasing the client count, and then we are unlocking, after which we are closing the client socket. And when we call the send message, we are actually executing this function, which is sending to all clients. We are locking because we're accessing the global array, and looping through all the clients, we are sending them that message, and we're unlocking. That's it. And inside the client part, we are creating two threads, send thread and receive thread. And after we create the socket, after we connect, we are creating the two threads that have two different routines, which is send message and receive message, with two different thread IDs, send message and receive ID, providing the same socket. So both of them are working with the same socket. And we are joining the two of them and then closing. And send message is sending the message as long as the client does not enter queue. And when they enter queue, it's just closing that socket and exiting. And when that closing occurs, inside the receive routine, the read will be returning as -1 error case, and then it will just also terminate it. And before that, we are retrieving back the socket file descriptor from the parameter, because it was passed as a parameter right here. Apologies, that right here. And after we retrieve it back inside the receive input routine, we are printing out whatever we receive as fputs right here. We are printing it out, and that is actually it. This is the input routine, and that is the output routine. Now that we understand how it works, let's try to compile and see in practice. What we'll be doing is we'll create one server right here and two clients, and those two clients will be talking to each other. Let's compile the source file gcc-o server chat server.c lp thread d and current. And then let's compile the client as well. Client.c. So now that we have compiled, let's run our server. So the server is ready and running to support all the clients. Let's connect one client. Client 127.0.0.0.0.1 to the port 4444. Kevin. Okay, so that Kevin will be the username of this client. And for the second one, let us connect also 127.0.0.1 4444. And for this client, sorry, but I will use one of your names, and I will just take a look at the Kakao room and use any name that I find. Oh god, this is difficult because Korean names, converting the Korean name into an English version, that's difficult. Okay, this seems easier. Okay, this seems easier. And I apologize if I'm writing this incorrectly. Okay, okay. I hope that I wrote it correctly because it seems easy, not difficult. Okay, and then, so the two clients have connected to the server. Let's try to send some messages and see that it's coming to the other client. And so let's say, hi, hey, how are you? So now that we have seen that the message is being transferred to other clients, we know that the multi-threaded server is doing its job by reading the message that's coming from one client and transferring back to all clients. So this is working fine. And the next thing that we have to check is actually how one client disconnects from the server, and then the server cleans up that socket file descriptor that is shared between threads. So it's basically this area when the client disconnects. So if this is also working fine, we will have no problem with the execution, and that means the chat application, the networking application will be finished. Let's connect one more client. 127.0.0.1 4444. For that, I will use one more name. Oh, this is okay. It's pretty easy. Okay, so IN. So now that one more client has connected and he can also send a message and everything is still working, let's make one of the clients to disconnect. For example, let me disconnect from this chat queue. So now that this process has terminated, will the server be able to handle these two? If it can, then our process is working all fine. Done, and it's working fine. So this is it, and this is where we were coming to throughout the Computer Networks Laboratory series, and hopefully you liked it, and please don't hesitate to ask any questions if you have through KakaoTalk or email, and I hope to see you soon. Bye.